Okay, perfect. So, Egbert, the floor is yours.
Yeah, thank you very much, Fernando, for the nice introduction. Welcome everybody, dear ladies and gentlemen. I welcome you to the webinar dealing with technologies for electromagnetic processing of materials. And I would like to show how these technologies are available and their possibility for savings of energy and carbon. The presentation I will do the next 45 minutes is a result of a project we have carried out in the last half year in cooperation with the Copper Institute, the European Copper Institute. And this has work has been done together with my colleagues Bernhard Ubenians. Please let me give first a short outline of my talk. I would like to start with a short introduction to explain the background, the content and the aim of this project. Then I want to focus on the very important primary energy factors and CO2 emission factors and their development in the next 50 years. We have concentrated our work on the European industry, on the EU 27 countries and the energy consumption industry there. And we have three different transition scenarios, how we can switch the fossil fuel heated processes to electromagnetic processes, to electrothermal processes in this time. We have selected 5 sectors which are important from energetic point of view in the European industry in order to demonstrate this possibility. This is the iron and steel industry, the non-ferrous metal industry, chemical industry, glass pottery and building materials industry, and paper and printing industry. And I will select some examples of these big or large industrial sectors in order to demonstrate our results. And finally, I would like to summarize the main results we have got in the frame of this project. Maybe for a first introduction, I would like to show some examples. This slide is unfortunately not complete. 2 pictures are missing. What are electromagnetic processing of materials applications? What are electrothermal applications for those attendants who are not familiar with this? In general, we are working with electric energy as a final energy carrier in order to use it for generating of process heat, in order to use the electromagnetic fields for generating heat, but also for generating forces which can be advantageously used in the processes. Some examples you can see here on this slide. This is on the left-hand side, a conventional resistance furnace which can be used instead of a gas-fired furnace. For example, we have on this slide something which has to do with heating of wires by conductive technologies, heating of tubes, for example, for bending the tubes, for shaping the tubes, but also using induction technologies for welding, for longitudinal tube welding, which is a very important process. In order to improve the surfaces of materials, the induction hardening process can be used, but we can not only heat, we can also melt material, for example, in the steel industry, in copper industry, aluminum industry, or we can also melt high purity materials in the cold crucible technology. But also laser processes are belonging to electromagnetic processing, conventional slab heating, but others like arc furnace heating, infrared heating, all these technologies are belonging to, let me say, electromagnetic processing of materials. And these technologies are able to substitute conventional gas-fired, oil-fired, carbon-fired processes. And this is what we are dealing with in the frame of this investigations we have done. Let me start with some background and some introduction. Fernando has told already some aspects in his introduction. In principle, electromagnetic processing of material provides significant opportunities for saving primary energy and reducing of carbon emission. Such investigations we have done already in the past, where we have directly compared different industrial processes regarding from the point of the final energy carrier. But in this presentation I give today, we will look forward to the year 2050. Today we can say that in Europe around 10% of the industrial thermal processes use electricity as a final energy carrier. And the industrial thermal processes cover, I can say, 2/3 of the total energy which is used in industry. So it's a very important sector from this point of view. You can ask yourself why. The main reason today are economic reasons, because the price for the kilowatt hour of gas, for example, is cheaper than electricity, and this is and was and is the main reason to use fossil fuel processes in this industry. In principle, we can say that electricity has the potential to replace up to 100% of other energy carriers used for thermal energy, for process heat, for electromagnetic processing. And this is also a very important point. And of course, if we look not only to the final energy, but also to primary energy factor and to CO2 emission, we have to take into account the primary energy factor. That means the ratio between the primary energy and the final energy. This is at the moment around at around 2.5, 2.4, but due to the increasing share of renewable energy in Europe, we can expect that this primary energy factor decreases from now 2.5, 2.4 down to, let me say, 0, or at least between 0 and 1. And this is also very important if we're speaking about the energy electricity. The aim of this work and the motivation of this work was and is the demonstration of the scope for energy and carbon-saving technologies in the EU through the use of electromagnetic processing of materials to show the potentials we have in this field. Therefore, of course, it's necessary to estimate the primary energy factor and the CO2 emission factor for electricity, and we are looking forward in the future to 2050, because we think that this is even now an important year, because normally the installations in industry, like big heating installations, furnaces for melting, normally are running 20, 30 years, so it's important to know what happens in the future. We have also investigated then 3 transition scenarios. how it could be possible to go from fossil fuel heated processes to electricity, to electrothermal processes. This I will explain also later. And we have looked to the most energy-intensive production processes, which are switched then to a situation with up to 100% of electrical operated industrial processes. I will also show which production processes we have taken into account for this investigation. If we look to the primary energy factors, that means the ratio, the amount of primary energy we need for 1 kilowatt hour of final energy, we can see that for the fossil fuel energy carriers like coke, for example, or gas, there is a primary energy factor which is around 1.07, or for coke 1.11. So we need 7 or 10% more primary energy than we need, but then we will get as a final energy. Of course, due to the conversion of the conversion process in power station, in steam power stations, the primary energy factor due to the Carnot efficiency is higher for electrical energy at the moment than for fossil energy. If we look to Europe, we can say that at the moment this factor is at around 2.4. That means we have an efficiency of about 42% of the power stations in average. But for sure we can expect an increased share of renewable energy in the future. In this case, of course, the primary energy factor will decrease. And how it could be, it's based on the different sources we can see in this slide, and we expect that in 2050 this primary energy factor is around 1.15 maybe. So this gives us an advantages for using electrical energy. So we can say that the primary energy factor for fossil energy can be estimated as constant. We can say that, of course, the primary energy factor for electrical energy depends on the energy mix, and it is based, of course, on a forecast of the European gross electricity generation with an increasing share of renewable energy. The similar things we can do, of course, with the CO2 emission factors. The CO2 emission factors, which is the number of CO2 emission, for example, in gram per kilowatt hours, which is generated, which is produced if we burn hard coal or if we burn coke or gas, to get an energy of about 1 kilowatt hour. So we produce 227 grams of CO2 if we get 1 kilowatt hour of gas, for example, energy of 1 kilowatt hours. Also this factor we can of course calculate for electricity, taking into account the power station mix of, for example, coal-fired power station, of nuclear power station, but of course also of the renewable power generation. And if we do this and we calculate this year by year, we get this curve where it's clear shown that the CO2 emission will drop down from now of about 400 gram per kilowatt hour electricity energy down to, let me say, 40 grams per kilowatt hour. So we can say that we will keep the CO2 emission for the fossil fuel in future as nearly constant, but we can say that the electricity, the CO2 emission factor for electricity, which depends of course clearly on the energy mix, on the mix of the power station, will be reduced due to the increasing share of renewable energies. These are the first from the generation point of view. Now we have to look to the demand side, to the use of the energy, and there we can see, for example, what are the consumers, what are the main sectors in the European industry who use the final energy in industrial processes. And the statistic shows different sectors, and we have selected the most, from our point of view, the most important, and from an energy point of view, most important sectors. This is the iron and steel industry, as you can see here, which used 18% of the total final energy in the European industry. We have also looked to the non-ferrous metal industry, mainly aluminum industry, for example. Then we have also looked to the chemical industry, which is using 20% of the final energy, the glass, pottery and building material industry, which is used 15%, and finally, in the frame of this investigation, we have also looked to the paper and printing industry, and of course mainly to the thermal processes in this industry. So we try to cover the most important sectors and to investigate the sectors regarding the transition from fossil fuel heated processes to electrical processes. And I will show later some examples from these sectors. In order to give a feeling what is about the share of energy, the demand of energy, we have investigated in our report. You can see here on this table first the 5 different branches we have looked at, and in these branches the sectors like steel industry, grey cast industry, aluminum industry. From the chemical industry we have looked to the plastic industry, we have looked to the glass, roof, brick, cement, lime industry, and to the paper industry. And here you can have some figures about the energy demand in these different sectors and the final energy demand of the branch we have investigated. And you see that we could cover, let me say, 87% of the energy used in the branch of iron and steel, only 3% because in aluminum industry, of course, we have a lot of energy used for primary aluminum, which is produced by electrolyte process, which are using already electricity. So we have looked to the secondary aluminum and covered only 3%. From the chemical industry, we have taken into account the plastic industry, 19% of the total energy share. A lot of thermal processes where it's possible to substitute fossil energy with electrical energy, we can find in the glass, pottery and building industry. So production of glass, roofs, cement, lime, this covers 99% of the energy in this sector. And for the production of papers, we have investigated the thermal processes, which cover around 52% in this sector. Only to give you an impression about what does it mean, what we will show later. In order to investigate and to show the potentials, we have created 3 different scenarios how to switch from 100% electrical processes to how to switch, from the current share to 100% electrical processes. So we have taken always the current distribution between electrical and fossil fuel processes, and then we developed the transition scenarios to 100% electrical processes. And therefore we are looking to 3 scenarios. The first one is a reference scenario. This implies no switching from fossil fuel heated processes to electrical. So we let everything as it is, and we will only change, of course, the primary energy factor and the CO2 emission factor, which depends on the generation, on the power station mix of electricity. In the second scenario, we assume, let me say, a linear scenario. That means a linear increase of the share of electrical processes up to 100% in the year 2050. Maybe this is the most realistic scenario, but to demonstrate what happens if we go very fast this step, that means if we go in maybe 5 years from fossil fuel heated processes to 100% electrical processes, we have also investigated a so-called shock scenario, which starts here in 2020 around and goes to 2025. Maybe this is, of course, not realistic, but only to show the possibilities, or what does it mean? Maybe the realistic situation is somewhere between these three scenarios. And along the scenarios, of course, we have then calculated what does it mean from final energy, primary energy, and CO2 emission point of view if we change the processes from fossil fuel heated processes to finally electrical processes by using electromagnetic technology. Let me start with some examples. The first one is the iron and steel industry, and this slide gives you an overview about the situation of the final energy carriers in the European iron and steel industry. And as you can see here, at the moment the share of electrical energy is about 21%. Of course, this includes not only using electrical energy for thermal processes. This includes as well electrical energy for drives, for example, in the rolling mills, etc. Everywhere where electrical energy is used for engines, for compressed air, etc. But all other energy carriers, means 79% of the other energy carriers, like hard coal, for example, like coke, which is of course used in the furnaces, and all others, including of course gas, which has also share of 30%. All other energy carriers, of course, are used for thermal processes or in the blast furnace for reduction chemical reactions. And what can we do in order to make this transition to electrical energy? If we look more in detail to the processes in the iron and steel industry, for example, in the production of steel in Europe, we can see that in principle we have two principal routes for the steel production. The first is of course the classical approach. That means we are using iron ore as a raw material. We go through the blast furnace to getting raw iron. We go to the oxygen converter and to produce steel finally. And this is used at the moment 78 million tons of steel are produced in this way. gives a share of 56%. An alternative possibility is to go to use scrap, of course, in order to use the electric arc furnace, to use electricity, or to use iron ore and to use the matrix process to use the direct reduced iron. And this is, of course, the input material in this case for the electric arc furnace, so we can use electricity here instead of coke on the other side. And at the moment, mainly this is coming from scrap. In Europe, 61 million tons are produced in this way. This means 44% are produced in this way. And in order to compare and to analyze the energy situation, the energy carrier, it's necessary, of course, to go more in detail. That means we have to look more in detail for the process of the blast furnace, which energy is needed, and you can see here. You can find from literature and from the process industry that for 1 ton of the crude iron in a typical blast furnace, you need this input materials. These are iron ore, cinder, coke, of course also electrical energy and scrap. And finally we get, of course, gas, which has to be also taken into account in the energy balance, which is recovered and which can then also be used later on. So this we have to balance with from energetic point of view, and then we get the next step after we get the crude iron. Of course, we have to produce steel. This is done normally by the oxygen blow converter, where we have also to do the energy balance for the oxygen converter, which is needed for 1 ton of steel. Of course, we need raw material, but we need oxygen, scrap, carbon, coke, and all these things has to be counted and balanced with the primary energy, has to be balanced with CO2 emission in order to make a comparison between these two different lines. On the other side, maybe more innovative way is to use the electric arc furnace, to use electricity as a final energy carrier, which is charged then, for example, with scrap, or which is charged with direct reduced ore. And here we have also to do the energy balance, what energy, which amount of energy is necessary for the production of 1 ton of steel in the arc furnace. And you can see here some average figures which show us the energy consumption of such a furnace. But of course, this is from mainly today mainly used for scrap. But we have, of course, also to produce from ore steel, primary steel, let me say, and this can be done with the help of the production of direct reduced ore. And this, of course, in this case, has to be enlarged. If we go this more innovative route, and this means we have to enlarge this process to produce direct reduced iron. And as you can see here, this is a typical example that, of course, in this case we cannot use directly electricity as a final energy carrier, because we need this reduction process. We need this chemical reduction processes or process of iron ore, and in this case today we use the natural gas. Of course, in future we can maybe also use biogas to save the resources for this process. But here we need an energy carrier not only to get the heat, to get the thermal energy, but also to have the chemical reaction in order to reduce the iron. This has to be taken, of course, also into account. If we now compare these different routes, the classical way and the more innovative way to go via the electric arc furnace, and we do this different scenarios I have explained, we can come to this result. Let us look first to the final energy. for example, we get a saving of 1.3 million kilowatt hours of final energy, which can be saved up to 2050. And if we use the shock scenario, of course, it is even more. Only to give you a bank with of the possibilities. So in this case, we can even say final energy, because we will change the process. We will see later, if we do not change the process, only the heat source, let me say, then we cannot save final energy. If we convert this results to the primary energy using the introduced primary energy factor, we can see here that also there we have a big potential in the iron steel industry to save primary energy. Yeah, it's an amount of 5.6 5,680 pentajoule, which is of course up to 2050 a big amount of primary energy we can save. And how it looks in detail, we can see along the curves the reference scenario, that means no switching, only changing the primary energy factor. We got the linear scenario, and we have here the shock scenario. And on the slide down, you can see the accumulated energy we can save using linear scenario or using the applying the shock scenario. And of course, it is possible from this also to calculate then the CO2 emission, which can be saved. And these results are showing on this slide. You can see that even also there we can save by linear switching or by the shock scenario a big amount of CO2, and the figures I have printed here on the slide. That means 1.4 million tons of CO2 can be saved by changing by switching the production route for steel, for example. And in this way, we have investigated also the processes in the other sectors. Another and very nice example how EPM, or electromagnetic processing technologies, induction technologies can be used is the cast iron industry, even maybe from energy point of view, it's much more smaller than the steel industry. You see the production rate is comparable small in comparison to steel, and but also there we have even today two competitive processes. This is the induction furnace process, which is using only 520 kilowatt hour per ton electrical energy, and the hot blast tubular furnaces, which is mainly used coke as an energy carrier, and even with modern furnaces needs near to double of energy, final energy, in comparison with the induction furnaces. But as I mentioned at the beginning of my talk, there are also economic reasons to use coke instead of electricity. Even today. And also this process, which has also some other advantages, using induction not only from the energy point of view, we can compare, and also here we see if we not only change the energy carrier, but if we really change the process itself, we can start to save also already final energy. And this is very, very interesting, but more maybe, of course, we look to the primary energy, and again, we can see that this switching gives us a big potential for saving energy up to the year 2000. Always interesting also to compare these results with the reference scenario where we have no switching, but due the changing of the energy, of the electric energy production due to the renewable energy, we get also here a big energy saving. And of course, we can have a look also to the CO2 emission, and we can see that to change only in this small branch of cast iron, we can save already millions of tons of CO2 emission. Even also in the aluminum industry, that means here the secondary aluminum industry, not the primary aluminum industry where we have the electrolysis process to produce aluminum. Here we are speaking about the secondary aluminum industry, where we make the remelting process, where we melting of scrap, where we make the alloying of the materials, the recycling industry. Also there we have always competition between the classical gas-fired furnace and the more innovative induction furnace. But as you can see here, today the main technology which is used is the gas-fired furnaces. This is not only a reason of price for electricity and for gas in comparison, but this is also a question of the one technology is established industry, the other is new, and therefore the induction channel furnaces is around 10% the share of the induction channel furnaces in the aluminum industry. So we got a big potential there in order to substitute the gas-fired furnaces. And as the same procedure as I have mentioned for the steel and the gray cast industry, what we can get is here in the save of final energy, as it is shown on this slide, by switching between these two technologies, and also a save, of course, in primary and in CO2 emission. I don't want to treat all these figures, all these numbers. Who is interested could find, of course, this presentations on the website. So you can study it, or she can study it more in detail later. The same situation, similar, we have saving of primary energy in the aluminum industry, and of course in the CO2 emission as well. Of course, the numbers are not the energy sector is much more smaller. Let's switch from the iron, steel, aluminum industry industry to the other sectors we have investigated. And I will show some examples from this. First is in Europe, all kinds of production of plastics, and we can see that the production of plastics was figures from 2007. This is 65 million of tons, and this is a typical value for the energy which is needed for production of plastic. This means we have a lot of thermal processes there also, and we can see here that in the production of plastic already, the electrical energy has a share of 61%. Also, of course, for drives, including, but also for heating, mainly resistance heating of the presses, etc., for the production. In this case, in the plastic industry, we have only changed the energy carrier. That means we have compared what happens if we go from the gas energy carrier to the electrical energy carrier, but we do not change the process. That means we do not use, for example, induction, which is not possible. We go from a gas-fired furnace, for example, to a resistance heated furnace. So that means, of course, we need the same final energy, and what results are coming out from this, to my mind, is very interesting, because if we only change the energy carrier, and we don't change the process technology, which leads to advantages, which leads to increasing of efficiency, of course, we will have no changing and no saving of final energy. Of course, we will use the same final energy for the process, as you can see here, independently, of course, from the different scenarios. And if you keep in mind the primary energy factors I have introduced, for example, for gas, which was 1.07 in comparison to electricity, which was is now 2.5 or 2.4. we can see that in the next 50 years, even we change the the energy carrier, we will not save primary